consortium led by Greg Wade, you know, and well, anyway, we've done a lot of stuff together, a collaboration of theorists and observers. So let me tell you a little bit the backstory of how I got into magnetic fields. There was this model by Joe Castanelli and John Brown that was called the magnetically torqued disk model. In order to explain BE stars, they wanted to use the moment arm of a magnetic field to propel things to Keplerian orbital velocity and then just let go. And what the problem is that Asif would do simulations and it never would just go into a Keplerian disk. And so I was on sabbatical. We had a wonderful time, Susie and I and the family. We were all in Scotland for a year. And he was a great host. And John is a real charming guy with a Scottish accent and stuff. But he was also very, very, you know, had strong views. And he thought the magnetically torqued disk was the right thing. So we have this meeting that coincidentally was in South Africa, the eclipse. And it was all about magnetic O, B, and A stars. And John Brown gave his idea about these magnetically torqued disks. And then Asif goes up and shows how this just doesn't work dynamically. And so I'm sitting at the table listening to these talks, and I'm sitting next to a guy named Detlef Grote. And he says, well, what about sigma or E? Now, being a stupid theorist, I didn't know what sigma or E was, but it was a famous star that showed H alpha emission, just like BE stars, but a very different profile for it. And so I basically said, tell me about this. And he told me that sigma or E basically had this double peaked emission. We'll come to the details in a minute. But the point is that I went back to Scotland. I said to John, your idea doesn't work for BE stars, but it will potentially work for these BP stars, these magnetic stars. He wasn't interested. And so I went to London for the second half of my sabbatical. I told it to Rich. And within a week, Rich had these beautiful, I mean, I already had done some preliminary calculations, but you know, Rich is a whiz with making these beautiful things. So let's go talk about, all right, so first of all, a lot of this is only possible because of Asif. Asif has done the hard calculations that allow me to have my, and when I ask him to do a whole bunch of models, he doesn't like say, yeah, I don't want to do that. He says, yeah, okay, you know. He's very cooperative, very willing to, you know, at least, you know, he'll argue with me, which is perfectly okay, but he doesn't just sort of dismiss it, you know? So he's just been a great collaborator. I don't know where I would be without Asif. He was my graduate student, and he became back to be my postdoc. He actually went to work with John Blondin for a couple of years. He actually, what happened was he had this beautiful poster of the AAS, and it was a whole year before he was supposed to be finished. You know, the year and a half he had to go. And John Blondin saw the poster and he says, can I hire him? You know, and I said, okay, go ahead. And he went to work with John for a couple of years did some stuff on supernovae. Then he came back to see him, to be with me. Okay, so here the idea, of course, is that there are two different kinds of magnetospheres. One is where the rotation is pretty slow, material gets trapped, then just falls back down on a dynamical timescale. We've heard about this before. Then you have these centrifugal magnetospheres where it gets trapped between the Kepler radius and the Alfvén radius. Oops. Yes. Gotta get used to this. And that's the so-called centrifugal magnetospheres. And now for the dynamical magnetospheres, there's this really interesting effect. I think Yale talked about this in her talk, that when you shock, you see now the wind doesn't get to flow away, it's forced to run into itself. And so that's called magnetically confined wind shocks. And but now, depending on how strong the density is, the shocks can cool very close to the apex, or they can basically, if it's lower mass loss rate, they'll cool back up here and they'll become softer because the wind will not have achieved high velocity. But this model gives you a prediction for how many X-rays you should get. And lo and behold, Gail Dazé took our predictions, put them on a observed X-rays versus this XDM. We had to reduce it by a large factor due to the duty cycle. But there they are. They're all falling over 5 orders of magnitude, almost 6 orders of magnitude. Beautiful relation. But there's these outliers, and they're all rapid rotators. So we still are in the process of analyzing these guys, why are they so much stronger in X-rays? We think it's because they don't have a low, I think it's because they don't have a very a low duty cycle. And I think it's also that the shocks are stronger because it's centrifugally accelerated. All right, so that's one of the problems out there. So here's also coup de grace, as far as I'm concerned. This is one of the most beautiful parameter study results I've ever been involved with. Basically, you increase the rotation. This is the rotation over the critical rotation on one axis, and you increase the magnetic confinement on the other axis, and you just collect material. You find out how much matter there is per unit radius as a function of radius and time. And you find that as you increase the confinement, the stronger you get more and more. This is the alphane radius. And you get, but it's not rotating, this just falls back down. But then if you increase the confinement with rotation, you start to form this layer, which is the centrifugal magnetosphere. And you're increasing this magnetic confinement parameter that was talked about earlier. This is still my favorite graph I've ever been able to, because it presaged this distinction between dynamical and rotational magnetospheres, presaged an observational diagram that in 2013 by Vero Petit, myself, many people, that you can put stars on this diagram where rotation increases this way, magnetic confinement increases this way. This is the place where they divide. This is where the Kepler radius and alpha radius. And there's all the stars up here. These all have centrifugal magnetospheres. They all show, a lot of them show 8 alpha. And here's the dynamical magnetosphere. And they're all O stars because they've been spun down enough that they don't confine. Okay, so now this also validated this incredible idea that Rich and I developed called the rigidly rotating magnetosphere. It's kind of a semi-analytic model that predicts where material will be collected. You can predict the H alpha variation. You can predict the spectral per-limit variation of the longitudinal field. You can predict as the clouds go in front of the star, they make little eclipses. All this can be compared with data. And then here is then what the RMM model, the rigidly rotating magnetosphere model, predicts in a dynamical spectrum. And Rich already showed this. And this is what you see in H alpha. And how many semi-analytic theories do you know that can do that? You know, it's pretty cool. All right. Now the question is well, we know how the magnetosphere is fed. It's fed by the stellar wind. How does it empty? And so there are a couple of different ideas. Well, for the dynamical magnetospheres, it's easy. It just falls back. But for the centrifugal magnetospheres, there's two possibilities. It just builds up, and it breaks open. It's centrifugal breakup. Or it diffuses because the magnetic fields are not ideal MHD. I worked on this a lot with Steve Cranmer. This is actually a graphic from a paper I wrote with Steve Cranmer when I was on sabbatical and visiting Colorado. But then here's the amazing thing that, again, one of the most successful theoretical analyses I've ever done. Matt Schultz has all this beautiful data on H alpha in emission. And then centrifugal breakout theory says that there's a magnetic field at the Kepler radius, which will allow you to confine enough material to become optically thick in H alpha. And right at that predicted level is when H alpha appears. Wow. and so, but there's this caveat for low luminosity stars, you don't see H alpha emission. Why is that? Is it because the field is kind of leaking a little bit? It's like filling a glass with a hole in the bottom. If you don't pour it in fast enough, it leaks out and never builds up. Or is it possibly that these are not H alpha, hydrogen doesn't get driven in these stars because the density is too low. And I think somebody, Joe, you talked about I think the ion coupling. Anyway, these could be ion runaway. So these could have metal winds. And you observers need to find out which one of those is the truth. Okay, so then Matt points out that, by the way, Matt is one of the best scientists I've ever worked with. And he has, if you ever get a chance to work with him and hire him, please, you should do it. Anyway, Matt also pointed out that a lot of the same stars that are radio emitter, H alpha emitters are radio emitters. And the ones that aren't, ones that are slow rotators are not. And so we came up with this idea. This is a figure that Matt came up with. I think it's very beautiful. The old theory says that the radio is being emitted, it's being formed by a particle acceleration in the current sheet that's above the tops of the magnetic field, but that doesn't have anything to do with rotation, so it can't be true. And our idea is centrifugal breakout, the reconnection that occurs with centrifugal breakout is accelerating electrons. Those electrons then drive right around the field and they make radio, incoherent, circularly polarized radio. And so not only does centrifugal breakout potentially explain the alpha, it also explains radio. And there's a scaling law that I derived, which fits beautifully with the observations. So Bernardini and I have been working on this, and we've gotten these models where we basically assume an injection of electrons high up from reconnection, and then just follow their emission. And it turns out they emit most of their radio back near the foot points. 5 minutes. Okay. I'm up 15. You're like Susie. Whenever she tells me to meet her someplace, she always tells me, you know, a half an hour earlier than I'm supposed to be there, because she knows that she's doing the Iwaki correction factor, you know. Okay, here's the other cool thing. Here's the other cool thing. These are the early type stars, and plotted. This is the observed radio, incoherent radio. Here's the ultra cool dwarfs. They're also rapid rotators. They fall in the same line, but they have a completely different mechanism for driving material into the magnetosphere. And there's Jupiter. So it suggests that there might be some commonality between magnetic fields of massive stars and magnetic fields of planets. So Bernardini is now trying to exploit this. Part of the idea is that the sun's magnetic field is very complex, but our fields are kind of dipolar-like, but so are the fields of planets. They're pretty dipolar. I mean, there's a little bit, there's the South-Manic anomaly and stuff like that, but the Earth's dipole is Earth's magnetic field is pretty closely a dipole, a little bit off the North Pole. Anyway, the idea is that the magnetic field of Jupiter is stressed by the wind pushing in, but there's also this source of plasma from Io. And so there's a commonality in the physics of wind-fed magnetospheres and Io Taurus. That's pretty cool. All right, so just a brief comment about